Hey there, science fans. Have you ever baked a cake or struck a match? Guess what? You've witnessed the wonders of chemical reactions. These fascinating processes are happening everywhere around us, transforming substances right before our very eyes. Atoms and molecules, the building blocks of matter, rearrange themselves, breaking old bonds and forming new ones. This rearrangement leads to the creation of brand new substances with entirely different properties than their original counterparts. Think about it this way. Imagine baking a cake. You start with separate ingredients like flour, sugar, eggs, and butter. Each ingredient has its characteristics, but mix them together, bake them, and voila! You get a delicious cake, a completely new substance with a unique taste and texture. That's the magic of chemical reactions. They're the reason we have things like medicine, plastics, and even the air we breathe. We've all been there, staring at something and wondering, is this a chemical reaction? Fear not, intrepid investigators, because I've got some surefire signs to help you crack the case. First up, let's talk about color changes. If you mix two clear liquids and suddenly, bam, you're looking at a vibrant hue, you've got yourself a chemical reaction. Next, we have temperature tricks. Chemical reactions can release heat, that's getting warmer, or absorb it, feeling chilly. So, if you notice a temperature change without any external heating or cooling, a sneaky chemical reaction might be afoot. Bubbles. Bubbles everywhere. If you see gas bubbles forming when you mix substances, that's another telltale sign of a chemical reaction. Sometimes chemical reactions like to make a grand exit, and by that, I mean the formation of a precipitate. This fancy word just means a solid forms when you mix two liquids. It's like a magic trick, but instead of a rabbit, you get a solid. So, remember detectives, keep your eyes peeled for these signs, and you'll become a pro at identifying those sneaky chemical reactions. Now let's talk about a scientific superstar who revolutionized our understanding of chemical reactions, the one and only Antoine Lavoisier. This brilliant French chemist gave us a groundbreaking principle known as the law of conservation of mass. In simple terms, Lavoisier's law states that in a closed system, the total mass of the reactants before a chemical reaction must equal the total mass of the products after the reaction. Think of it like this. Imagine you have a box containing Lego bricks. You can build all sorts of awesome structures, but you'll always have the same number of Lego bricks inside the box, right? Lavoisier's law is crucial because it helps us understand that atoms are merely rearranging themselves during a chemical reaction, not magically appearing or vanishing. Chemical reactions are not just confined to laboratories, they're happening all around us. Let's start with the heart of many homes, the kitchen. Baking a cake is a prime example of chemical reactions in action. Now let's zoom out to factories. These powerhouses rely on chemical reactions to produce a vast array of products. From the mundane to the extraordinary, these molecular transformations shape our daily lives. Section 5. Reactions that rock the world, photosynthesis and combustion. Now let's talk about two chemical reactions that are not just cool but essential for life as we know it. Photosynthesis and combustion. First up, we have photosynthesis, the incredible process by which plants convert sunlight into chemical energy. Plants use chlorophyll to capture light energy from the sun, converting water and carbon dioxide into glucose, a type of sugar that provides them with energy to grow. Photosynthesis is like a natural solar panel, providing food and oxygen for countless organisms, including us humans. Now, let's move on to combustion, the chemical reaction that gives us heat and light. Combustion occurs when a substance reacts rapidly with oxygen, releasing energy in the form of heat and light. Think about burning wood in a fireplace. The heat from the fire provides warmth, while the light illuminates the room. Combustion is also essential for our cars, power plants, and many other technologies that rely on burning fuels for energy. Section 6. Energy in the mix, endothermic versus exothermic reactions. Hold on to your hats, science fans, because we're about to unravel the mysteries of energy in chemical reactions. You see, chemical reactions can either release energy, making things hotter, or absorb it, making things colder. Let's start with exothermic reactions, the energy-releasing rock stars of the chemical world. These reactions are like tiny explosions, releasing energy in the form of heat, light, or sound. Think about burning a candle. The flame releases both heat and light, indicating an exothermic reaction. Now let's cool things down with endothermic reactions, the energy-absorbing ninjas of the chemical world. These reactions are like ice packs, absorbing energy from their surroundings and causing a decrease in temperature. Think about dissolving ammonium nitrate in water. This reaction absorbs heat from the surroundings, making the solution feel cold. So remember, every chemical reaction involves either releasing or absorbing energy, making the world a more dynamic and exciting place. Section 7. Types of reactions. Putting chemical changes into categories. Chemical reactions are like dance moves. They come in different types, each with its unique steps and style. Let's break down some of the most common types. Combination reactions. These reactions are like a romantic pairing, where two or more substances combine to form a single, more complex product. Decomposition reactions. These reactions are like a breakup, where a single compound breaks down into two or more simpler substances. Single replacement reactions. These reactions are like a game of musical chairs, where one element replaces another element in a compound. Double replacement reactions. These reactions are like a square dance, where two compounds exchange partners, forming two new compounds. Understanding these basic types of reactions helps us predict the products of a chemical reaction and write balanced chemical equations. Keep those thinking caps on, stay curious, and keep exploring the world around you. Section 8. Chemical equations. Writing the language of reactions. Chemists use a special shorthand called chemical equations to represent chemical reactions. These equations are like recipes listing the ingredients, also known as reactants, on the left side and the final dish, or products, on the right side. For example, the chemical equation for the reaction between hydrogen and oxygen to form water is 2H2 plus O2 yields 2H2O. The numbers in front of the chemical formulas are called coefficients. They represent the number of molecules or moles involved in the reaction. Balancing chemical equations is crucial to ensure that the number of atoms of each element on the reactant's side equals the number of atoms of that element on the product's side. Chemical equations are powerful tools that allow chemists to communicate and understand chemical reactions in a concise and standardized way. Section 9. Predicting the outcome. What happens when chemicals collide? Predicting the products of a chemical reaction is like solving a puzzle. You need to consider the properties of the reactants and the type of reaction taking place. For example, if we mix an acid and a base, we know that they will neutralize each other, producing salt and water. Similarly, if we heat a metal carbonate, we know it will decompose to form a metal oxide and carbon dioxide gas. We can also use the periodic table to predict the products of single replacement reactions. Elements in the same group, or vertical column, of the periodic table tend to have similar chemical properties. Predicting the products of chemical reactions requires practice and a good understanding of chemical principles. Remember, chemistry is all about exploring, experimenting, and making connections. Section 10. The mighty mole. Counting atoms and molecules. In chemistry, we deal with tiny particles like atoms and molecules. Counting them individually is impossible, like counting grains of sand. That's where the mighty mole comes in. The mole is a unit to express the amount of a substance. 1 mole represents approximately 6.022 times 10 to the 23rd particles. Think of a mole like a jumbo-sized pack of atoms or molecules. Section 11. Moles and mass, connecting the dots in chemical reactions. Remember Lavoisier's law of conservation of mass? Well, the mole concept helps us apply this law to chemical reactions. Since atoms are neither created nor destroyed during a chemical reaction, the number of moles of each element in the reactants must equal the number of moles of that element in the products. This principle allows us to perform stoichiometric calculations, which involve using balanced chemical equations to determine the amount of reactants or products involved in a chemical reaction. Stoichiometry is an essential tool for chemists, allowing them to predict the amount of reactants and products needed or produced in chemical reactions. So, the mole concept and the law of conservation of mass go hand in hand, helping us understand the quantitative aspects of chemical reactions and their applications in the real world. Section 12. Chemistry. It's a wrap. Congratulations, science explorers. You've journeyed through the fascinating world of chemical reactions, from identifying their telltale signs to understanding the language of chemical equations. We've explored the energy transformations involved, the different types of reactions, and the importance of the mole concept in quantifying chemical changes. Remember, chemical reactions are happening all around us, shaping the world we live in. From the food we eat to the clothes we wear, these molecular transformations are the backbone of countless processes that make our lives possible. Stay curious, keep exploring, and never stop asking questions about the world around you.